So we're talking about, we did one example, how to calculate the molar mass using data about a sample of gas. So we'll do this next example. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 Celsius and a pressure of 976 millimeters of mercury. Find its molar mass. Okay, this is what I consider to be a fairly challenging problem for Chem 3A students. It's probably not immediately obvious what you're supposed to do. So when you get a problem where it's not obvious what you should do, then you have to kind of pick it apart and think about it. Always a good strategy to write down the numbers. So we'll try starting with that. We've got 827 milligrams, and we've got 0.270 liters, and 88 degrees Celsius, and 976 millimeters of mercury. Let's identify what we can. Well, millimeters of mercury, that's the pressure, so I'll call that P. 88 degrees Celsius is the temperature, call that T. 0.270 liters is a volume, let's call it V. Bless you. 827 milligrams. Well, we've got pressure, volume, and temperature. We're dealing with a gas. This is probably going to involve the ideal gas law, right? Ideal gas law, PV equals nRT. So we've already found pressure, volume, and temperature. R is a constant. Is 827 milligrams related to N? Is it the number of moles? No, it's the number of milligrams. Could we figure out how many moles from the milligrams? If we knew the molar mass, we could. Do we know the molar mass? That's what we're trying to find. Okay. Well, what do we need to find the molar mass? The molar mass is the number of moles divided, the number of grams. It's grams per mole, right? So we need a mass of the sample and we need the number of moles. Well, this is definitely related to the number of grams, right? We could convert that to from milligrams to grams. We put milligrams on the bottom and grams on the top. Milli means 10 to the minus 3. So this is 1 times 10 to the minus 3 grams is equal to 1 milligram. We do the math and we get 0.827 grams. I'm going to move that over. Grams per mole. So we know the number of grams, 0.827 grams of the gas. We need to know how many moles there are. Oh, that's what the N is, right? N is moles of gas. We know the other letters there, PV, R, and T, so we could use that to calculate the number of moles. And then we can plug it into this equation. Are all of these units on the pressure, volume, and temperature, are all of those correct for ideal gas law? No. The volume's okay. The temperature needs to be in Kelvin, so let's convert that. Plus 273. Out the calculator. 88 plus 273 equals 361. And what unit does the pressure have to be in? Atmospheres. So I want atmospheres on the top and I want millimeters of mercury on the bottom. The relationship there is that 1 atmosphere is 760 millimeters of mercury. So 976 divided by 760, 1.28. My original pressure had 3 sig figs. The conversion is exact. I should have 3 sig figs here. I don't want to introduce rounding errors, so I'm going to carry 2 extra digits. There's my pressure. Let me get this out of the way. So we had our equation PV equals nRT. We want n by itself. So I want to divide by r. R's cancel out. Divide by t. The t's cancel out. That leaves me with n by itself on one side of the equal sign. In order for this to remain one side equal to the other, I have to do the same thing to both sides. And that's how I rearrange my equation. I end up with n equals PV over RT. And now I can plug my numbers in. I've got 0.270 liters. Well, yeah, that's fine, but it's not the pressure, is it? Pressure is 1.28 for 2 atmospheres. Write your units in here. 0.270 liters. Down here, I've got R, 0.0821 liter atmospheres per mole Kelvin. It's the units on R that tell us what units the pressure, volume, and temperature have to be in. And then we've got the temperature, 361. You got to be careful when you do the math here. Put brackets around those, or parentheses when you do the math. Most students prefer to multiply the 0.0821 times 361. If you put parentheses around it, you'll be okay. Otherwise, you're going to get a crazy large answer. So on the calculator, 1.2842 times 0.27 divided by, open parentheses, 0.0821 times 361, close the parentheses, equals. So n is equal to 0.0116989 moles. How many significant figures does that number have? Or should it have? It should have 3. Remember that these leading zeros are not significant figures. Okay? So the 1 is the first sig fig, and the next one, and the 6. So I'm just going to underline that because I'm not to the final answer yet. I don't want to round things off. So I'm going to plug this in up here, 0.0116989 moles. So I've got 0.827 divided by 0.0116989 equals, maybe I should go back to red up here. So the molar mass equals 70.690 grams per mole. If we round that to 3 significant figures, we're going to get 70.7 grams per mole. And there's the answer hiding in the middle of the slide. Well, actually, it's not in the middle. It's way over on the side. Is that a reasonable number for a molar mass? It's a positive number, and it's 2 or larger, right? Hydrogen is the smallest element, and so you can't have a molar mass that's less than 1 gram per mole, and hydrogen's diatomic, so it's actually 2. Any questions? Well, gas behavior depends on the conditions. We talked about the ideal gas law, and that applies to an ideal gas. Gases don't always behave in an ideal fashion. So we're going to look at the difference. So here are ideal gas conditions: high temperature and low pressure. Under these conditions, gases behave as we expect them to. The particle size is very small compared to the space between the particles because they're at a low pressure, so there's a lot of space. So then the size of the particles doesn't matter at all. And the interactions between the particles are insignificant. When these guys run into each other, they're moving so fast that they just bounce off of each other. But we can put a gas in a situation where it's not going to act according to the ideal gas law, and this would be a situation with low temperature and high pressure. At low temperature, the molecules or particles slow down, and so when they're moving and they bump into each other, they're not moving as fast and they have time to actually interact a little bit. There are forces of attraction between all particles. And so when the gas particles are moving more slowly, they're going to be a little bit sticky to each other, and that's going to affect their behavior. So we've got some intermolecular attractions going on. With high pressure, under high pressure, you push all the molecules closer and closer together. When the particles get very close together, then the size of the particles begins to matter. Did I give you the Fresno versus Wyoming analogy? No? Okay. So, one summer we were driving to Minnesota with too many children in the van, and we're driving through Wyoming, and this was before cell phones, so we're looking through the AAA guidebook and looking at Wyoming, and the population of the entire state was about the size of the population of Fresno, right? The area of the state, much larger than the area of Fresno. It's not like Rhode Island or something. It's a relatively large state. So that makes me think about gases because I'm a chemist and I'm weird. So in Fresno, the people are much closer together, right? In Wyoming, they're very, very spread apart. So the people in Wyoming are more like a gas, and the people in Fresno are more like a liquid. And then you squeeze them together even more, and then they might be a solid, right? So that's one analogy. And then taking that to where I want it to go gets a little weird, so I'm going to switch it up a little bit, and we're going to look at people in an elevator, okay? So people in an elevator. People in an elevator, they're very close together. Not unlike this high-pressure situation where the gas particles are now forced into close contact. Over here, you've got the people in Wyoming, they've got the whole state to spread out in. Does it matter how big the people are? No, it doesn't. They could all be 500 pounds. There's plenty of room. They could all be 50 pounds, little children. There's plenty of room. The size of the people doesn't matter. Okay, now put them together, get them closer, talk about people getting into an elevator. Now does the size of the people matter? It does matter. Because they're so close together, there's not much space in between. When you squeeze a gas, put pressure on it, you're forcing the particles closer and closer together. Now the sizes of the particles start to have an impact. A gas under regular conditions, there's so much empty space that it doesn't matter. Does that make any sense? That was a very poor presentation of a crazy analogy. Sorry about that.